I will make a start. So let me quickly share my screen and just let me know once you're able to see it. Okay. Can you see the slides? Yeah. Okay, cool. So, Patty, I would not be able to see the chat, so would request you to call out if there's anything on the chat which needs my attention. Okay, cool. So,
Don't worry. If I say something, I will let you know.
okay, cool. Thank you so much. All right, so I'll start with a brief introduction about myself. Hello, everyone. Uh, I am Nishi Ajmera. I am a lead engineer working with Publicis Sapient. I'm also a public speaker. I've spoken at various GDG platforms. I talk about LLM, LLM ops, and various JavaScript frameworks. Also, I'm a woman tech maker ambassador. So, yeah, that's me. Uh, let's move into the agenda. So the agenda for this boot camp is I have divided it into 4 weeks. So the first week, that is today, we are going to talk about the fundamentals of LLM, what large language models are, how they came into being, and what are the key terminologies which you need to know. Then next week we'll get into fine tuning, and then next week we'll get into prompt engineering, and last week we'll build our own large language model, and we'll try to deploy it as well. So I hope by the end of this 4 week bootcamp, you have a fair understanding of how LLMs work, and you are able to build your own LLM and deploy it as well. Uh, just to mention over here, it's good to have a basic understanding of machine learning and Python. But even if you don't have the basic understanding of machine learning and Python, it's all right. I'll try to simplify the concepts as best as possible. Okay. So let's get started. So what are large language models, right? So large language models are a type of machine learning models that are trained on a large data. When I say large data, how large is the data over here? So we are talking around petabytes of data here. Okay. Then the next thing is LLMs are used for natural language processing tasks such as text generation, question answering, language translation, and things like that. I hope everyone here would have used either ChatGPT or Bard. It has been there. It has become a part of our day-to-day lives now. So you know how cool that is. So LLMs are based on deep learning neural networks such as transformer architectures. We will get into the basics of neural network and transformer architectures in a bit. So another main point to know about large language models is at core, it is just trying to predict the next word in the sentence. That's all the LLMs are doing. Okay. So moving on, what is a neural network? Okay, so neural network is an inspiration from our brain. So what we have tried to do is we have tried to analyze how our brains work, and then try to put that into a machine learning model. So the best way to understand what neural network is to take an example of how our brain works and then try to put it here. So let's take an example of, let's say, you are trying to make a decision of whether to go to beach or not today. So our output here is we are trying to predict whether we can go to beach today or not. Now, if you're planning to go to beach today, there would be some influencing factors to it. One may be whether how is the weather outside, whether do you have trains or not. So the transport is a very big factor for you to go to the beach. And then another influencing factor can be the activities. So for me, I look for activities if I go outside, like water sports or something of that sort. So let's say we have these three influencing factors which would decide whether we would be able to go to the beach today or not. So these three influencing factors would be our input. Now let's try to see how our brain works to determine the output of this. So if we talk about the influencing factors, let's say weather. Now, if how important is weather in determining whether you'll be able to go to beach today or not. So if the weather is sunny, yes, I'm definitely going. If the weather is cloudy, maybe I will go. So I would put a weight of around let's say 3 to this one. Then coming to transportation, for me, transportation is very important. So it will have a high weight. So I will put a weight of 5 to transportation. And activities, I am okay. Even if there are no activities, I would still want to go. So I would give a weight of 2. So here we have assigned this a weight of 3. Here we have assigned this a weight of 5. And here we have assigned this a weight of 2. Now, what would happen is, so if let's say the weather is cloudy, I would still want to go. So this would become 3 into 1 1. Then is transportation, is train, are trains running? Yes. So if this would become 1 into 5, and the 5 would be the output over here. And then are there any activities which I can do? No. So this becomes 0. So this becomes 2 into 0 2. So the output of this would be I think probably 8 or something. And let's keep a threshold of, let's say, 4. So if the value is greater than 4, that means it's a yes. So that means I'm going to the beach today. So I hope this gives you a fair understanding of, how the weights and biases work. Now, coming to the neural network. So neural network has 3 layers to it. One is the input layer, the second one is the hidden layer, and the third one is the output layer. Okay, so as we spoke, we gave the input parameters over here. Then in the hidden layer is where all the computation activities happen. This is where the neural network tries to learn things and then generates the output. So this is a very high level overview of how neural network works and you know uh, how it reflects the behavior of a human brain. Okay, moving on. So before 2020, there were many neural network architectures which were in being, I mean, which are still in being. But there were neural network architectures for each task. So if I talk about computer vision, or let's take an example of object detection. So for object detection, we used to use this model which is known as convolution neural network. So what convolution neural network will do is it uses filters to basically detect the object. I'll not go too much into detail of how CNNs work, but that's what it does. Okay, then we had recurrent neural networks. The recurrent neural networks were used for natural language processing. We will go into a bit more detail on recurrent neural networks in the further slides. Similarly, we have deep belief networks for speech related tasks. We have sequence to sequence for translation related tasks, and so on. But after 2020, everything is transformers. So let's get into it. Let's get into the transformer architecture. Now, before getting into the transformers architecture, we need to know why transformers even came into being. Okay, so to understand that, we need to understand how recurrent neural networks work. Okay, so recurrent neural networks are neural networks that are good at modeling sequence data. Okay, so when I talk about sequence data, uh, text is a form of sequence data. So let's say if I am asking a question, what time is it? If I'm asking this question to a chatbot, that is basically a sequence data which the chatbot has to process. But before getting into this, let's look at an experiment of how our brain processes sequence data. So I would ask you to say A to Z alphabets in your mind. Give it a try right now. I hope it would be fairly easy to just say A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R till Z. I think it's fairly easy to do that. But if I ask you to reverse that, if I ask you to, say the alphabet in the reverse order. So Z, then I think it's Y, and then it is pretty difficult for us to do it in reverse order because that's now how we have learned. From the childhood, we have learned ABCD in that sequence, right? Let's take another fun example. So, what if I ask you to say the sequence from F? So, say the character next to F. Well, I need to do it like A, B, C, D, E, F, then G, H. And once I am at G, H, then I can continue easily. So, why is that easier for us? So, because our brain learns sequence patterns, right? If we know the sequence, then we are good at predicting what's coming next. The same thing RNN does for processing data sequentially. So they have something called as sequence memory. So what RNNs will do is RNNs process data one word at a time. Okay. So if you see over here, this is the recurrent neural network. And let's take this example now. So we ask the chatbot, what time is it? Okay. So we feed the first word to the neural network. So we feed what generates an output. Okay. Then we feed time to the neural network. Now here what happens is it will take the context of what over here, and then it will generate the output, because we need the context to figure out the answer to that question. Okay. Then the third word is. Now we feed is to the neural network, and then is will take the context of time and what. Then we feed it, and then it will have the context of is, time, and what. And then the last character is question mark. So question mark will have context of what time is it, all of it. So sorry. So if you see the color distribution here in the question mark, you will see that it doesn't have it has very less context of what. So that is essentially the problem with RNN. The problem with RNN is because we are sending context sequence by sequence, it forgets what it has learned initially. So till the time it reaches the question mark, it has almost forgotten the context of what. So that is why it has difficulty in processing long range dependencies. So these are the shortcomings of recurrent neural networks. The first shortcoming is that it processes data sequentially. Now, when it processes data sequentially, you cannot throw a lot of GPUs to it to make the processing parallel and fast, right? Then the second shortcoming is that it has difficulties in processing long range dependencies. It has limited contextual awareness. Okay. And then the last one is that it does not do parallel processing well. So that's where transformers came into picture. So transformers was first introduced in this paper, which was called attention is all you need. Okay. So what transformer architecture introduced was it introduced these three main functionalities, these three I would say logic. So these three concepts, sorry, my bad. So transformer architecture introduced these three concepts. The first is positional encoding, attention, and self attention. Attention was there even before this paper was introduced. So the main concept which this paper introduced, and which basically changed how the large language models work, is self attention, and we will see how that works in the future slides. Okay. Transformers is an encoder decoder style architecture. Uh, we will also look at the encoder decoder style architecture in the next slides. So, coming to positional encoding, what does positional encoding mean? So, we saw in recurrent neural networks that RNNs process data sequentially, token by token, right? Now, what we are doing here in transformers is we take the input, we convert that input into the vector form, and then we add the positional details also to the input. So what we are doing here is, let's say our input to the model is I love the transformer model. Now we have broken this input into tokens, and then these we have created the vector of each token. So this is the vector of I, this is the vector of love, this is the vector of word the, and then along with this we are adding the positional value as well, the positional vector as well. So the positional encoding is the idea that instead of looking at the word sequentially, you take each you so instead of looking at the word sequentially, you feed the sorry you add the positional value to the input before you feed the input to the neural network. So you store the information about the word order in the data itself rather than in the structure of the network. So then when you train the network on a lot of data, it learns how to interpret these positional encodings. All right. So moving on, let's now understand what an encoder architecture is is in the what is encoder in the transformer architecture. So let's look at this bit over here. So we provide input to our tra- we provide input to our model. So let's take an example of a chatbot here. Let's say we enter, hi, how are you? We send this text to the chatbot, and we are expecting a response from the chatbot as I am fine. So now when I send this input, our input here would be, hi, how are you? Okay. Now this input is sent to this input embedding. What this input embedding is doing, it is just converting those words into vectors. That's all this bit is doing. Now once we have that vector available with us, we add the positional information over here in the form of positional encoding, the thing which we saw in the previous slide. Okay. Now the output which we get over here, this output is fed into this multi-head attention module. So there are two modules over here, multi-head attention and the feed-forward module. We will have a close look at how this multi-head attention works, because attention is all you need, and attention is the main concept which basically changed the way LLMs are working, and how LLMs have become so efficient, right? So once we have the vector over here with the positional encoding done, we split that vector into three parts. So we create a query, key, and value over here. These query, key, and value are nothing, it is the clone of the input vector which we have gotten over here. It is the clone of the input vector. We have created three clones. But just to give you a brief of what query, key, and value is, so if you take an example of YouTube search, so if you go on YouTube and you search for a video, uh, you type in something like video on LLMs, right? So your query would become whatever you're searching, whatever text you're searching. It will use that query, and then it will search in the database. It will search for the keys. So key here would be your video titles and description, right? And then if the key matches, it will fetch the video. So the video would be the value here corresponding to the key. So coming back to the query, key, and value, so we basically clone the input into three clones, and then we do a dot multiplication here. So the query dot multiplication of query and key. Okay, when we do a dot multiplication, it gives you a 4 cross 4 matrix over here. Okay, so if just bear with me for this entire thing. I know this might be too overwhelming or a lot of information, but I promise you this would make some sense once we go through this. So yeah, sorry. So we were here. We do a dot matrix dot multiplication over here for the query and key, and it gives you certain numbers over here. What the output here is the attention. It basically gives you the attention weights. So these numbers basically define how. So I'll take this example. This number determines how much attention this word "are" should give to this word "how," or how much attention this word "you" should give to "high." So it basically determines these value. This is what we are getting over here. So the score which we get over here is highly inflated, and we want it in the range of 0 and 1. So that's where we take the vector, we do a softmax to it, and then it gives us the numbers in range of 0 and 1. Now this is the attention weights which we have got, and these are nothing but these are just giving the words context to it. So how how much of weight should you give to high, how much of weight should you give to how. This matrix is basically doing that. Now once we get our attention weights, we multiply the attention weight with the value which gives us the encoded output. So this is what the output which gets generated out of the encoder. Okay, now encoder architectures are used for understanding of text, right? So the 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 process which we discussed over here till the attention weight, this basically is attention process. Okay. Now what happens in multi-head attention is, so when we are generating our these query key value, right? We split this query key value into n vectors. So you can understand it in a way like we are creating n clones of this, and then each clone goes through a self attention of its own. Each clone goes through a self attention of its own, and it generates an output, and all of that output, all of that is basically sent into the multi-head attention, and then it generates uh, the final encoded output. I hope this makes sense. I know it can be a little overwhelming, but it's good to have this knowledge. It would make things easier in our further slides. Okay, so we get our encoded output over here. Let's now try to understand the decoder architecture. So what happens in the decoder architecture is basically used for text generation. Encoder is used for understanding of the text. Decoder is used for generation of the text. So since it is used for generation of the text, let's start from here. So in our example, we entered "Hi, how are you?" Now we are waiting for a response from the model. So here in the output, the first uh, input over here would be an empty character. It would send an empty character to it. We will create an embedding on this. We'll add the positional encoding, and then it goes through the same multi-head attention process which we discussed in the previous slide, and then that output goes over here in this block. Okay, now if you see here, one value is coming from here, and then there are two arrows from the encoder architecture. So the key and the value are fed in here from the encoded output which we get, and we had query key, value, and query, right? And so key and the value are fed from here, and the query is here, and then it then goes into the multi-head attention, and then the same process happens, and then we get an output. Okay, so it will generate an output as empty token and the word "I." Now that empty token and the word "I" is again fed to this decoder architecture. It will take now two characters as input, the empty token "I." It will feed that here. It will again take the encoded outputs from the encoded architecture. These encoded outputs it will feed in here, and then it will generate another character M. So this goes in loop until it receives a N token, and that's how it generates the output. So if you see here, we feed in start, then we feed in start I am, then we feed in start I am fine, and then we get this end operator over here, and that's when the process stops. Okay. I think that's enough. I'm not going to go into more detail of how the decoder works, but uh, on an on a high level, it's better to have an understanding of encoder and decoder. And just to repeat, encoder tries to understand the text, decoder helps to generate the text, and encoder understands the text using the attention weights, which we spoke about, right? So here is another example of attention. So if we take an example of converting an English text into French, so here the English text is: the agreement on the European Economic Area was signed in August 1992. We want to convert this English text into French. Okay, so when we are converting the English text into French, if we do word by word conversion, the conversion in French would not make much sense, because the tenses in French are different from the tenses in English. So if you see over here, just focus on these three characters: European Economic Area. So if you see here, the conversion of European is based, it has to take the attention, it has to take the focus of it has to take these two characters also in consideration before converting European into French. So if you see,
Nishi,
sorry.
sorry for interrupting you. So people is sharing in the chat that we cannot see your cursor, and I
Oh,
you're,
okay.
yeah. So I believe you are using it to pinpoint certain
Yeah,
areas.
yeah, yeah, right, I'm doing that. Oh, can you see my cursor now, or is it not visible now as well? Because I
No, we cannot see it.
oh, okay.
I don't know if yeah, I don't know which could be the best way to
Okay,
go.
I think I mean, to be honest, this was the last part where I wanted to use the cursor.
Okay, so maybe it's fine, and
I
we
mean,
can get it ready for the next session.
yeah, yeah, yeah. For the next session, I'll just have a look at it, why it's not working.
All right, thank you.
Thank you. Okay. So I will, yeah, I will just probably wrap it up in wrap the slide quickly. So basically, yeah, so while conversion, we need to have those attention weights, and those attention weights basically help us to position the words over here. So in English, European Economic Area comes like one after the another, but if you convert that into French, the European comes after economic. Okay, moving on. So let's talk about language models. So there are basically three types of language models, which we are going to talk about here: autoregressive, autoencoding, and combination. So autoregressive models are models like GPT. These are the models which are good at generating text, and they follow the architecture, decoder part of the transformer architecture. Auto encoding models, as an example mentioned over here, is BERT. So they are good at understanding the text, so they are good at tasks like classification, and these models follow the encoder part of the transformer architecture. Then we also have we also have combination model. So an example of combination model is T5. So combination model has both encoder and decoder, follows both encoder decoder architecture, and these are good at translation tasks, right? So enough about the transformer architecture. Now let's get into how LLMs work. Okay, so just So pre-training is an important step in in the working of large language model. Every LLM on the market has been trained on large corpus of text data and on specific language modeling related tasks. So during pre-training, the LLM tries to learn and understand the general language and relationship between words. Okay, so if I take an example of BERT over here, BERT was pre-trained on Wikipedia and book corpus. So book corpus is a collection of fiction and non-fiction books, and BERT was pre-trained on two specific modeling tasks. One is masked language modeling task, and another is next sentence prediction task. Okay, so during this pre-training phase, the LLM tries to learn the general language and it tries to learn the relationship between words. Okay, also some of the LLMs like GPT, they are trained on proprietary data sources, which gives edge to the parent company over their competitors. But it is worth knowing how these models were pre-trained, because pre-training enable us to apply transfer learning, which lets us achieve state of art results which we want. So that leads us to our next term, transfer learning. So what does transfer learning mean? Transfer learning is a machine learning technique that harness knowledge acquired from one task to enhance performance on another related task. So what does this mean? So transfer learning is basically what language has learned during the pre-training phase, take that learning and apply it to the downstream task. So if you see over here, if we take example of BERT, so during the pre-training it learns the general concepts like language, and then you can use that learning to do downstream stream tasks such as question answering, or sequence classification or generation of text and things like that. So the core idea behind transfer learning is that the LLM has already acquired substantial knowledge of language and word relationship, and this existing knowledge then serves as a foundation for improving performance on new tasks such as text generation or text classification. So, transfer learning also significantly reduces the amount of task specific data needed to fine tune an LLM for a new task when compared to training the model from scratch. All right. So, moving on to fine tuning. What is fine tuning? Fine tuning involves training the LLM on a smaller task specific data set to adjust its parameter for a specific task at hand. So if you see the example over here, if you want to fine tune an LLM, what we do is the first step is to figure out which model we want to fine tune and also the fine tuning parameters. Then we aggregate some training data. Okay. Uh, we feed the training data to the model and then we compute loss. So what does loss mean? Loss is a measure of error. So it is basically determining how far is the predicted output from the actual one. Okay. uh, so yeah, loss is a measure of error, and then we determine gradient. We compute loss and then gradient. So gradient is information about how to change the model to minimize the error. So with the help of gradient, we figure out uh, what biases to feed into to minimize the loss. And once we compute the gradients, we update the model through back propagation, and then we try to minimize the loss. Okay. Then coming on to tokenization. So we'll see all of these. Uh, we'll do hands-on on these concepts in the next session. Today is just I'm just trying to introduce all these terminologies to you so that it would be easier in the next session to understand how the LLMs are working when we are doing fine-tuning or prompt engineering or tasks like that. Okay, so then moving on, tokenization. Tokens are the smallest units of understanding and understanding in an LLM's vocabulary, and it can represent word, punctuation, characters, or even subwords. So if you see the diagram over here, uh, so we are providing this as an input to our model, demystifying tokenization, the building blocks of language AI. Now, if you see how the tokens are created, it has broken down demystifying into three subwords, and then tokenization has also been broken down into two subwords. So basically, we are taking the sequence and then breaking it down into smaller words or subwords, which can then be fed into our model. Okay. So yeah. And next is embeddings. So embeddings, we did see a bit of it in the transformer architecture, but embeddings are nothing but a mathematical representation of words. So we saw we converted these tokens into vectors. That's essentially what embeddings is, and we can add information to the embedding, like we can add the positional information as form of positional embedding. Uh, we can also capture the semantic meaning in the form of embedding. So embedding are used to represent words, phrases, or tokens in a way that they capture semantic meaning and relationship with other words. Okay. Now, coming on to modern LLMs, I got a really cool GIF over here, which basically shows you the evolution of LLM, how it started from the models which it started. So if you can see here, GPT-1 came in 2018, GPT-2 came in 2019, along with BERT, Roberta, and then GPT-3 came in 2021. And then after GPT 3.5, like when Chat GPT came, and there was a boom of language models, and you can see all these models over here. uh, One of the points which I wanted to highlight over here is all these models are trained on minimum of 10 million or 10 billion parameters, usually around that or more. Okay, so we saw how LLMs work. Now, let's move into the challenges. What challenges does LLM have? And one of the main challenges of large language model is cost. It sounds very fancy to use, to create to create a LLM of our own, or to train an LLM of our own, but it has its own cost. Like there are a lot of opportunities, but when it comes to deploying LLM, it is challenging. And uh, if you see the number of projects which are going on, the number of uh, large language models which actually make to production, it is like, I think 60%, 60, no, I think 60% don't make it to production. I may be wrong. I mean, I may not be like accurate over here in terms of fact, but it is around like 40 to 50% LLMs, only 40 to 50% LLMs make it to production. So one of the main challenges is cost. And so building and training LLM is expensive because it requires GPUs, and it requires parallel processing. It requires a lot of power, to basically a lot of power and infrastructure to basically train a large language model from scratch. So if I can give you a view of how much I think Chat GPT cost, how much just the training of the foundation model of Chat GPT cost, I think the cost was over $100 million. So I mean, yeah, that gives us a view of how costly it is. But one of the ways to overcome this is to use open source pre-trained models. So nowadays we have a lot of open source pre-trained models which we can just use it and then fine tune it as per our requirements. The cost of fine tuning LLMs then again depends on several factors, including the model size or the amount of data used to fine tune it and the computing resources as well. So we are going to see how we can fine tune an already pre-trained model as per our requirements in the next sessions. Okay. Then moving on, one of the common challenges faced uh, by large language models is hallucination. So I hope everyone would have heard of when Bard actually came in, and then there was a factually wrong statement, which on the day when Bard was released, I think there was some factually incorrect statement which was generated, and there was that was in news all over. But also, if you see on the slide over here, so let's just take the example which is there in the first box. So we feed this query to the chat box where we say the Bob's wife is Amy, Bob's daughter is Cindy. So who is Cindy to Amy? And the answer is daughter-in-law. It doesn't say the chatbot will not say that it doesn't know. It will just confidently give you a wrong answer, right? If you see another example over here is if you give this prompt like explain RLHF for LLM, and it has given the answer as rights, limitations, and harms and freedom. I think, yeah, I think the image is a little blur, or probably I'm not able to see too clearly as well. But so the problem here is LLMs will generate text. It will just make anything up, and that has been a major problem. I also remember I was doing a research on one of the topics. Like I was doing a research on how AI has influenced, or how AI. Just give me a minute. Yeah, how AI has been useful in women's security in India. And I was trying to do some research on that, and I asked ChatGPT for pointers, and ChatGPT made a very good story of some made up app which is used in India and everyone is using it. And it actually gave me data also, like after this app came out, uh, the crime rates went down and all those. It was a very perfect story which I wanted to hear, but none of it was true. So yeah, hallucination is a major challenge in large language models. We will see how we can avoid hallucination. There are certain techniques which we can use uh, to to minimize hallucination. We will see those techniques when we are looking at prompting and fine tuning when we move on to those topics. But one of the reasons why LLMs hallucinate so much is also the data quality. So it also depends on the kind of data where on which the LLMs are trained. So I cannot just remember the name of the language model which was trained on the Reddit data, and the information on Reddit may not be, like, all the information on Reddit may not be true. So that is one of the reasons of why LLMs hallucinates. One of the many reasons. So another challenge in large language models is bias. uh, Bias is there within us, I mean within us as a society, so that basically flows into the large language models as well. So if you see over here, we have historical bias, we have representation bias. So historical bias is basically which is already there in our data. Like I'll give you an example of so uh, if we take an example of normal, let's say, sorry, just give me 1 second. So yeah, a historical bias, we take an example of, let's say, if we ask a chatbot to give us an images of a doctor or image of a housewife, so what would the chatbot do? The chatbot would generate uh, for doctor, it would generate you a male image. If you ask a chatbot to generate the image of a CEO, it will generate a male image of a CEO. It will not think of generating a female image. So things like that, which are there in which are very prevalent in our society, that basically flows in our models as well. And we can take certain actions on how to minimize bias. We will look at those as well in the next sessions. So I think I would stop over here because I think it is a lot of information for the first session. So if there are any questions or feedbacks, I'm happy to take it.
Thank you, Nishi. I can see that there are some questions. Um, so this one, in the decoder, the multi-head attention layer has one of the three inputs from the output layer in itself and two other inputs from encoder. How does the values from encoder influence the final output of decoder?
So the values from the encoder has the attention matrix in it, so it has the context to it. So let's say when I think we were talking about hi, how are you? So to respond to that question that I am fine, it needs to understand that it is a question and it is asking you how are you, like. So it is basically uh, giving that context to the decoder of what question has been asked, if that makes sense.
All right. Another thing over here, someone is curious about what you think is driving the hallucination issue.
So hallucination, there are a lot of issues. One of the main issues of hallucination is the data. So if you're like I gave an example of some large language model was trained on the data from Reddit. Now there are so many incorrect information online. If we use those information to train our data, then uh, I mean it would predict incorrect output. And let me go through that slide if I can. Yeah, and also in a way, if you look at large language models, they're basically just trying to predict the next token for you. So whatever they, I mean, I think it is also lack of context which may sometime lead to hallucination.
Yeah. We have more questions over here. How do you deal with bias?
How do we deal with bias?
Yes.
So again, dealing with bias is, again, it comes to data. So one of the thing is data. We have to be there are certain steps which we can do while doing the pre-processing of data. We will go into the life cycle of LLM in the next session, where we'll see what are the pre-processing steps which we do. And during those steps we can take certain actions to reduce the bias. That is one such action which we can take, uh, which I can think of at the moment. Yeah, but I'll try to cover this in the next session more.
All right. Someone is asking why not just have a method of saying we have no response or sorry, please try again.
So it does, LLMs does give you, I mean, it does generate that response. But the thing is, if you play with the prompts, then it will again, try to generate. So LLMs are not that smart, I would say. We still, I mean, LLM still needs to be evolved in terms of learning. Probably, if we give it few more time, I'm sure it would become smart enough.
Yeah, they're not that smart yet.
Yeah.
Could you explain how the vectors are formed? Is it representing a word or sequence something else?
How vectors are formed. So I mean, there are basically libraries or methods in Python which would just, generate the vectors out of it. I am not too sure of the underlying like logic of how they are being generated.
Maybe we can have a look at it and share it.
Yeah. Surely I can have a look at it and come back on this one.
Yes, Joe, this will be recorded and it will be put up on the Glasgow GDG Glasgow YouTube channel. Can you recommend any good books on this topic?
Yes, I think I did read one of the books on O'Reilly. I think it was a quick start guide to large language models. It is very easy to read. It won't like you won't feel overwhelmed with all the concepts which are there. So yeah, you could give that a try.
Okay. Yeah, well, they're really great comments on the chat. It would be great if you read them. And yeah, thank you everyone for joining us tonight. Thank you, Nishi, for preparing this amazing bootcamp. You will receive, after the session is done, you will receive an email with a form for your feedback. That is very important for us and important to Nishi because that will allow us to get your feedback and to make these sessions better. So please be honest with your feedback is the best way for us to improve and to keep on organizing these free online sessions with a bunch of different experts in different domains in technology. So yeah, thank you so much for being here. Thank you, Nishi, again.
Thank you,
And
Patty.
yeah,
And I just wanted to say one thing. I know today's session was very theoretical, but I promise next sessions will have more hands-on things because we were just getting started. So I know it would have been a little overwhelming today.
yeah, and it's important to have at least a proper understanding of the basics, and
Yeah.
then you all can have some base to keep on researching on your side, and then coming again to the next session of the bootcamp and start building up your skills.
Yeah.
um Recommendations for work homework, something that they can start doing until the next session.
I would say get your basics, like get the Python basics right, I would say.
All right, that's
Because yeah, we would get into code in next session, so that would be good.
amazing. Well, thank you, Faye, again. And a big shout out to everyone that is joining us from the Google Developers Online community in Discord. And yeah, I hope that you all can have a great weekend and let's see you next week.
See you all next week. Bye.
Bye bye.